Did you know that cancer resulted in nearly 10 million deaths in 2020? Being a leading cause of death worldwide and the second leading cause of mortality in the European Union, it is a societal challenge that calls for orchestrated, transnational, and interdisciplinary efforts from various actors. Because cancer affects us all in one way or another, investment in cancer-related research is key. Hello, and welcome to the second edition of Crosstalks, a podcast series by the UT Austin Portugal Program that will walk you through the wonders of science-business collaboration. We'll be exploring emerging topics in the areas of advanced computing, medical physics, nanotechnologies, space-earth interactions, and technology innovation and entrepreneurship, as we delve into the program's groundbreaking industry-driven research projects. Today, we will talk about proton therapy. But what is proton therapy, you may ask? Well, the University of Texas MD Anderson Cancer Center in Houston defines proton therapy as a 196-ton cancer-killing machine that uses protons instead of X-rays and that can target a patient's tumor with a sub-millimeter precision while sparing nearby healthy tissues and minimizing side effects. A simple yet powerful definition that depicts what is distinctive about this method compared to conventional therapies such as radiation, surgery, chemotherapy, or immunotherapy. The idea of using protons in medical treatment dates back to 1946, with Robert Wilson proposing to use accelerated produced beams of protons to treat patients with deep-seated tumors. The first attempts to apply protons in treating cervical cancer patients began in the 1950s in nuclear physics research facilities. Applications were, however, circumscribed to a few areas of the body. In the late 1970s, imaging advancements, coupled with the development of sophisticated computers and improved accelerated and treatment delivery technology, made proton therapy viable for cancer treatment. Nevertheless, we would have to wait until the 1990s to see clinical centers with proton beam facilities emerging and expanding worldwide as precision, personalized medicine hastened pace. Like any advanced therapy, proton therapy brings some challenges, one of which is measuring the distance protons travel to the tumor cells. Indeed, the extreme precision of proton therapy may be significantly impaired by several factors, including errors in positioning the patient in the treatment room. For instance, in head and neck cancers, this can be particularly problematic since it typically takes a ring of detectors surround the patient to get accurate measurements, but some relevant geometrical constraints may compromise this accuracy. Positron emission tomography, or PET, is increasingly considered a reliable imaging method to support treatment plan correctness. The UT Austin Portugal TOF-PET for proton therapy project is therefore working on a new type of PET scan, showing how tissues and organs are functioning to understand what the prescribed dose of proton should be and whether they are traveling to the right spots to fight off cancer tumors. I'm Shel Habib, and today our guests are Stefaan Tavernier, co-founder of the company PETsys Electronics, and Karol Lang, professor of physics at the University of Texas at Austin. Welcome, Stefaan and Karol, and thank you very much for accepting our invitation to participate in this podcast.
It's a pleasure to be here.
Thank you.
Okay, now, Shana, thank you very much for giving us a chance to talk to the general public. We think that's important that you do that, and we are glad that you give us a chance to do that.
Thank you. So I have already briefly explained what proton therapy is, but can you, Karol, explain to our listeners how it works and where it really stands in comparison to other existing therapies to fight cancer?
With pleasure and briefly.
Thank you.
Proton therapy is based on different than other therapies principles of energy deposition and thus the fight of the tumors or cancer cells. Unlike in conventional therapy where photon beams are used, the proton beams deposit the energy in tissues in a very different manner. It was discovered more than 100 years ago by William Bragg, and in fact, together with his son, they shared a Nobel Prize for not this particular discovery, but the discovery of for their studies of structure of materials through X-rays that were discovered just a few years earlier. And through studies of alpha particles, Bragg and his son, William and Lawrence, discovered that when alpha particles were stopping in matter, they were effectively depositing most of their energy at the very end, immediately towards the stopping point of their trajectory or path in the tissue. And that principle is behind the proton therapy, because in photon irradiations, that phenomenon does not exist. It is the energy deposition doesn't have a well-defined spot in the tissue where it deposits most of energy, while in protons that happens, and that makes a much cleaner incision of the destructive power of the irradiating beam of the cancer tissues.
Thank you. Stefan, would you like to also share your views?
It was very clear. No, I don't think.
It was very clear as well.
Yeah,
Thank you.
What you said is very interesting, Karol, but there is an ongoing heated debate about proton therapy, right? Advocates of evidence-based medicine argue that more high-level clinical evidence is needed to prove the superiority of this therapy over conventional treatments and therefore justify its high upfront costs. On the other hand, those in support of proton therapy claim that, by sparing normal tissue, proton therapy may have fewer side effects than conventional radiation, and that proton therapy patients are able to maintain their quality of life during and after treatment. This is expected to reduce the overall economic burden of cancer. What are your stance on this debate, Stefan?
Yeah, well, of course, proton therapy equipment is a very expensive piece of equipment, and it's perfectly normal that people say, hey, is it really justified? Now, there are a few things that I can say about this. First of all, there are different treatments for cancer, and maybe it is not as true as you like. I mean, sure, popular is very expensive. People may think that chemotherapy is very cheap, right? You just give the patient a few pills and that's it. That's very cheap. Actually, if you study this, and it has been studied, then chemotherapy is actually more expensive than conventional radiotherapy, and not say more expensive than proton therapy. So maybe you get a little bit of wrong picture if you do not know this. But nevertheless, proton therapy is an expensive equipment, and it is expensive. Now, there seems to be an international consensus that in a population of about 10 million, there are enough patients for which the benefits of having proton therapy compared to conventional therapy justifies the extra expense of this machine. And this is, of course, the reason why in Portugal it has decided to go for that, because that's about the size of population you need to justify the expense.
Okay.
Let me add that I strongly believe that economic sides of our endeavors are clearly important down the road, but I think it is important to present opportunities and possibilities for treatments and how it is incorporated into various economical structures of health coverage and health insurance. It's probably, unfortunately for politicians, but I think it is the duty of, I feel, duty of researchers to advance possible technologies and present them to for the society to use or utilize in the best way they can do.
Thank you both. I definitely agree, and like what you said regarding the duty that researchers have to advance technologies and offer them to society despite the possible high costs. Now, I'd like to understand how the UT Austin Portugal TOF-PET project fits into this technological landscape supporting the advance of proton therapy clinical practices. Can you tell us more about the project's underlying challenges and the envisaged solution, Karol?
Sure. The project is to build an instrument that would assist the proton therapy at MD Anderson in terms of providing feedback how efficient, how good therapy irradiation is happening. This is a very challenging goal. Nothing has been done in here worldwide to the extent that you can sort of push a button and get the feedback. So what we are doing is building a small pilot experiment in which we would exploit the beam of the MD Anderson and expertise of many experts that come together to do this. And this is not different than what I do normally in my other sort of Monday to Friday research, because for me, this is more of a spin-off of my normal research. And in elementary particles, in experimental particle physics, we always bring many experts together to build larger experiments and larger instruments. And in here, it's a similar process. The instrument may be small, but it does require a spectrum of expertise. And that's what we actually were lucky to assemble and have now, both from MD Anderson, Portugal, and UT Austin.
Thanks, Karol. So, as far as I understand, patient studies are not part of the present application, but will be part of a follow-up project after successful conclusion of this one. But the current project will allow testing the developed system with phantoms and small animals at the MD Anderson Cancer Center, right? So, how long and bumpy the road towards TOF-PET results commercialization is? How long will cancer patients have to wait to benefit from your solution, Stefaan?
Yeah, so the present project is a 3-year project, and so we are about halfway. So in sort of little less than 2 years, we should have finished that. And basically, this is, I would say, a technical test. Right? We are not, as you say, have patients, but we will have all the things that will allow us to see the technical problems and study them well enough. And at the end of the project, we will have a fairly clear view of what kind of problems that still need to be solved. Now, of course, it's not something that there are enormous risks. It's not that the answer will be that it will not work. No, it's not that. It is that we'll say, okay, we told you like this, but it turns out it's a bit better like that, and so on. So this is basically where we will stand at the end of the project, where we will, of course, publish the results, and I think we will come to the conclusion that this is a method that can work, and then we will have a better idea of certain technical hurdles that will be there. And then we will need to build a new version of the system that then would be able to be used for real patient in the case of head and neck cancer, because their detector can be smaller. If you want to do other organs in the patient, you need a much bigger device that would again be much more expensive. So, but I think the second phase, again, 3 years, looks like a reasonable estimate. So I would say then after 3 years, after the end of this project, and probably some time to get new funding, and 3 years later, we could come with a report where we really have treated a number of patients, and hopefully that will be convincing enough that the medical doctor then in the end will have to take the decision to adopt that, will be convinced that he really should go like that and use it for patients. So that gives you a kind of idea. So it takes time. All those things, those technical develops, and everything is possible, but it takes time and effort.
Wow, that is exciting that in 3 years your PET scan will hopefully be ready. Thanks for sharing those exciting news with us. So, the uniqueness of this international consortium, academics working side by side with doctors, technology developers, and business people. What's been like working with such a diverse team, Karol? How do you transform interdisciplinary into a strength?
Right. So, as I mentioned, my background is experimental particle physics, where we bring many experts together to design and fabricate quite sophisticated and complex instruments that are used for basic research. Here, I think the portfolio of professions is even wider, broader, and I like it. I'm learning quite a bit from places and from people and on subjects that I knew very little about. So it's a challenge in a sense that we all need to contribute to the same and advance the same project. But I think it is pretty well understood by everybody what needs to be done. So in the end, I'm actually perhaps surprised, but there are really no big obstacles from the point of view of bringing all together all these experts from really different walks of life.
That's amazing. Thank you. Stefan, would you like to add anything?
I think this is perfectly correct. I would say I've been always working in international collaboration all my life. So certainly working with colleagues in the US or so, that I've always done, and that has never been. Now, there are cultural differences, not say that they do not exist, but they are not to the point that they create problems. I mean, I have always been working together with people from in Europe. I take, for example, Italy and Sweden, for example. The culture is really very different in those two countries. And it's really noticed that, but that doesn't create a problem in the collaboration. What is a bit more difficult, and not it's a problem, it's a bit more difficult when you talk to medical doctors, right? Because they have, of course, a completely different view. They know a number of things that we don't know, and we know a number of things that they don't know. And it is not always easy when we talk to them to make sure they understand what we are trying to say, and then probably they think that we are not understanding what they are trying to say. But that is certainly a bit more difficult. And not say it's a problem, but there I would say it is not so easy. They're really very different worlds, and the communication is not so easy. There are a few exceptions, by the way. There are a few medical doctors, and I know a few that are really technically very knowledgeable, and they certainly exist, right? But they are not that common. And then it gets a little bit not so easy to explain what you're trying to do and how things you should look at things.
That makes sense. So
yeah, let me emphasize what Stefan is saying, that indeed the international aspect of the collaboration is not an issue. I think that nowadays the research tools are so universal and so broadly applied everywhere in the world that this is not an obstacle in any way. There are cultural differences, as Stefan is pointing out, and I completely agree here that the biggest maybe challenge is to to interact with the medical side of the project, but we haven't gotten there fully yet. So this is actually something ahead of us.
I'm sure that when you get to it, you'll be able to deal with that challenge. So we are nearing the end of our conversation, unfortunately, but I'd like to ask you both this final question. Beating cancer is a global commitment and effort. How important international science and technology programs, such as the UT Austin Portugal one, are to allow research to be translated to clinical practice and industrial products? Stefan, if you want to start.
Yeah, well, I think I can only say that's very important because these are highly complex technical developments, right? And if you would imagine we would do that as a pure Portuguese project, develop it only in Portugal, then we would have, and in Portugal, would have to bear the cost of this development alone. And then in Portugal, there will be only one system because there's only one Proton accelerator. So this in the end would be a hugely expensive thing, right? I would say that would make no sense. So it has to be international on one hand because we pool knowledge that exists in different parts of the world, that's one thing. But also, if this has to become economically meaningful, I mean, that's a machine that has to be sold all over the world and not just in Portugal. I mean, this is so niche market that if you would just sell it in one country, that makes absolutely no sense. So for both reasons, completely different reasons, for both reasons, it's absolutely essential that you have this kind of international collaboration. I could not imagine doing it otherwise.
Thank you. Karol, would you like to add anything?
Absolutely true, and I exactly agree with that. It is essential that we conduct such research, and I think that the fact that it's broad and international is just inevitable because of the complexity of the project itself. I actually would like to recognize here the vision with which this program is being conducted here. I must say that this was a hugely and pleasant, huge and pleasant surprise to me, how this funding was arranged and how we are free to do what we do. I must say that I wish that many other funding agencies were as I would say wise as this program is for us here. So it is both essential and I think I'm very optimistic it will produce very good results for the future therapies.
Great. Thank you very much, Stefan and Karol. Very exciting news. It was a pleasure to chat with you today, and we are very happy to hear that the UT Austin Portugal program was able to help bring your project to reality. Thank you all for listening to this episode of Crosstalks. If you enjoyed it, and even if you didn't, we would love to hear from you. So make sure to subscribe and leave a review. For additional content, follow us at UT Portugal on Twitter or visit utaustinportugal.org. The TOF-PET project consortium is made of 6 partners: the PET Electronics, the University of Coimbra's Laboratory of Instrumentation and Experimental Particle Physics, the Center for Nuclear Sciences and Technologies from the University of Lisbon, the University of Texas at Austin, and the University of Texas MD Anderson Cancer Center. The TOF-PET for Proton Therapy project is co-financed by the European Regional Development Fund through the Operational Program for Competitiveness and Internationalization, COMPETE 2020, the Lisbon, Portugal Regional Operational Program, Lisboa 2020, and the Portuguese Foundation for Science and Technology, FCT, under UT Austin Portugal. The total eligible investment is around 2 million euros, with a public funding of around 1,700,000 euros. The UT Austin Portugal Program is a partnership program in science and technology between the Portuguese Foundation for Science and Technology and the University of Texas at Austin, supported by the Ministry of Science, Technology and Higher Education in close collaboration with the Council of Rectors of Portuguese Universities.